Hello there, this is a geometry video. It is chapter 10, section 1, and we will be talking about circles and circumference in this chapter. So first and foremost, I want to give you a definition, if you will, of what it means to be a circle. A circle is the locus, or basically the center, or set of all points in a plane that are equidistant from a given point. So, for example, here we have point C being the locus or the center, and basically, if I were to take any distance from this point to the circle, then all of those distances would be the same. So any point that is equidistant from this center is going to be on the circle, and that's how the circle is formed. So there's also well, I already mentioned it here. It says from a given point called the center. So we call this point the center. So my circle kind of looks like an oval. That's because it's kind of distorted from the image on the board. But keep in mind, it is in fact circle, and they're all equidistant. So some key concepts that you need to have probably in your notes are these definitions down here. I want to give you some information about how we name circles and stuff. So a radius, and if you have more than one radius, the plural version of radius is radii. So a radius is a segment that has endpoints at the center and on the circle. So your point would be here, and on the circle, that would be a radius. So if you look at this diagram here, a radius would be something like the segment CE, also segment CF, and also segment CD. So as long as the two endpoints of the segment are the center and on the circle, then those would be examples of radii. A chord, not like a guitar chord, okay, but a chord is then a segment with endpoints that are on the circle. So any segment that has two endpoints that are on the circle is considered a chord. So for example, this segment here from D to E, this segment here is considered a chord because it has two endpoints that are on the circle. But also AB is a chord because it has two endpoints that are on the circle. But specifically, because the segment DE not only has two endpoints on the circle, but also happens to be passing through the center, then it's a special chord, and we call that a diameter. So a diameter of a circle is a chord, but it passes through the center and is made up of collinear radii. So collinear meaning the same line. So the radii CD and CE are collinear. And so those are some of the definitions, vocab that you need to have as we go forward. You'll also notice from this information here how we name circles. We draw basically a circle and then put a center inside of it, and that's our symbol for circle. So if I say circle P, then I would go something like that. Or if you prefer, you can actually write out the word circle P. But that would just take longer, so who would want to do that? So anywho, that is the first part of what we're going to do. So we're going to go to some examples here. And here in example 1, we have name the circle and identify a radius. Now in this diagram, there's actually more than one radius. To name the circle, as we said before, the center, we're going to name the circle by its center. I probably didn't mention that before, but you need to name it by it. We can't call this circle L. Because the center is P, we're going to call it either center P or, not center P. We're going to call it circle P. Getting away from myself here. Circle P, or draw the circle with the center in it and circle P. So much easier. Circle P for the naming the circle part. And then identify a radius. We have several radii here. We have actually 3. You only need to list 1. But I'm going to go ahead and give you all 3. So we're going to start with the center. So we have a segment that goes from P to N. But we also have PM. And then we have PL. So 3 separate radii. You don't have to name them all. When it says give a radius, you only need 1. But in case you all picked a different one, there you have all the 3 that you could have picked. In part B, identify a chord and a diameter of the circle. For chords, you actually have 2 chords. This is not a chord because it only has one endpoint on the circle, and not the other endpoint is not on the circle. So JK is a chord, but technically so is HG, because it's also got two endpoints on the circle. And so for the first part, JK or HG would work. Now when it asks for a diameter, then you would actually have to only list HG. HG is the only chord that goes through the center of this diagram. So here we have two different chords and one diameter. So we're going to let you now try one on your own. Name the circle, a radius, a chord, and a diameter. So I want all four things in this example. And once you have done that, we can move on to our next key concept. And our next key concept is about radius and diameter relationships. And so by definition, the distance from the center of a circle to any point on the circle is always the same. We talked about that in a circle, the distance from the center to any point on the circle is always the same. So all the radii are the same. And so what we have now is that all radii are congruent. So that means that a diameter is composed of two radii. We talked about how one diameter has two radii in it and it's collinear. That means that all diameters of a circle are also congruent. So that means that if I were to draw a diameter as any segment that goes through the center, right? So I can draw diameters here all day long. I could go, there's a diameter, diameter, diameter. Any of these diameters will all have the same, they would all have the same distance. They'd all be congruent. But more importantly, we have two different ways of looking at this. So we know that a diameter, this is the easy, the diameter is going to be 2 radii. And if we take that formula and just very quickly divide both sides by 2, then we would get that R equals D divided by 2, which is basically what our formula over here says. If you want to find the radius and you're given the diameter, all you have to do is divide it by 2, or basically multiply by a half, same thing. Or if you're given the radius and you want to find the diameter, all you have to do is double it. So that's basically what that's saying, so it's not very complicated. So here we have in example 2, QV equals 8 inches. So we know that this distance here is 8 inches. And it wants to know what is the diameter. Since we're given the radius, it makes more sense for us to use this formula. So we're going to say that the distance is equal to 2 times the radius. And since the radius is 8, we know that the diameter is 16 inches. And just like that, we have found our diameter. So now you can do it-yourself number 2, where they're giving you the information here of TU, using the same diagram. They're giving you what TU is, the diameter, and they're asking you for the radius of, and I didn't put here, but there should be circle Q there. And then if QT equals 11 meters, what is QU? So there you go, you can do that, and we'll move on to our next concept. All right, so now we're talking all about circle pairs, all right? So basically, you have 2 circles are congruent if and only if they have congruent radii. So if 2 circles have the same length of radius, then those 2 circles are going to be congruent. And then we have all circles are similar, since similar just means they have the same shape. So all circles have the same shape, so all circles are similar. And then we have the more important one, which is concentric circles. Concentric circles are circles that are coplanar, so they're in the same plane, and they have the same center. So you can see that here in this example where circle A with radius AB versus circle A, the big one here, with radius A to C. So those 2 circles will be considered concentric circles. So these circles can intersect in 2 different ways. Each method has 2 different ways. So if you're going to have 2 points of intersection, these are some examples of what that might look like, where the 2 circles are kind of overlapping, and so you have 2 points of intersection. They can also have 1 point of intersection. So that could happen like this, where these 2 circles are describing a situation where we would call this tangent. The 2 circles are kind of touching, but in 1 point, but they're not overlapping. Versus this scenario, where the circle is inside the other, but don't confuse this with concentric. In the case of concentric, they have the same center, the both circles, one inside the other, but they have the same center. Here, clearly, this smaller circle's center is not the same as the bigger circle's center. So they don't have the same center, but they do have this point in common where they're touching here kind of in a tangent way there. And then, of course, there's no points of intersection where the circles are not overlapping at all. They're totally in different places. Or one circle is inside the other, like in the case of the concentric circles. They don't have any overlapping parts, so there's no point of intersection, even though they have the same center. Remember that the center of a circle is not technically part of the circle, because it's not on the actual circle itself. It's just kind of giving you a reference point. So those are the ways that we can have intersections. So we're going to go to our example here so I can show you kind of how we're going to apply this. In example 3. And so what you have to know is that the segment that connects the centers of two intersecting circles contains the radii of the two circles. So let me just say that again, and then I'll maybe show you with the diagram. The segment that connects the two centers of the intersecting circles. So here's a circle, they're intersecting. There is a segment that is connecting the radius of this circle with the radius of that circle. That segment would be RS in this case. So we're referring to, when I say the segment that's connecting the two concentric circles, or sorry, the two intersecting circles, that segment we're talking about is RS. So in that segment, what we know is that that segment contains the radii of both circles. So the segment RS contains the radius of each circle. And that makes sense because here's my segment, and the radius of circle S is from here to here, so C to S. And the radius of the other circle is R to D. Correct? So that's all it's saying. And now they're asking us to do some work here. It says the diameter of circle S is 30 units. So for the bigger circle, its diameter is 30 units. And then, so for circle S, we're just going to go here. For circle S, I know that the diameter is 30 units. If I divide that by 2, then the radius is 15. Just some information to note. Okay, then we have the other circle, circle R. In circle R, the diameter is 20 units. And if I divide that by 2, then the radius of circle R is going to be 10. Just some things to keep in mind. And in addition, they're telling me that ds equals 9. So in addition, we know that ds equals 9, and they want us to find CD. So here is point C and point D. So what we know is that the segment that goes from C to S, and this is going back several chapters ago, to the segment addition postulate, which basically says that if one segment is split into two different pieces, if I add those two pieces together, it should equal the whole. That's the segment addition postulate. So what I know is that the segment that goes from C to S, is equivalent to C to D plus D to S. And since I know that C to S is the radius of circle S, and the radius of circle S is 15, then I can put 15 in its place. CD is what I'm asked to find, and DS I was told is 9. So now I can subtract 9 from both sides, and I know that CD is equal to 15 minus 9, or basically 6. So 6 units. And that is how I find the value of CD. So now you are being tasked with finding the value of RC in do-it-yourself number 3. Then we go on to our next key concept, which is circumference. And circumference is basically the equivalent to perimeter for figures that are not, what would we call them, like polygons. So the difference between, like, the perimeter would be like if you had a triangle, you would be finding perimeter because you've got sides. You have, a rectangle, you've got 4 sides. You can find the perimeter by finding the distance around. Polygons all have sides. Any figure that has sides, you're going to be looking for perimeter. The problem with a circle is that there aren't any sides. It's about the smooth round thing, right? So you can't we don't call it perimeter anymore, we call it circumference. But it's kind of the same idea where area is the stuff inside the figure. Circumference or perimeter is the distance around. It's just a matter that in the circle's case there are no sides, so you don't call it perimeter, you call it circumference. But anywho, we have two ways of finding a formula for circumference, because we know from before that we have, by definition, the number pi is a ratio of the circumference of a circle to its diameter. So we know from way back in the day that the C over D is equal to, if I can write this correctly, it'd be nice, is equal to pi. Pi is an irrational number, and if you take any circle's circumference, so if you measure it all the way around and divide it by its diameter, you will always get roughly 3.14159, blah, 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 blah. So that's what we know. And so if we take this ratio and solve it for C, because we want to find a formula for circumference, we would just go times D, and we would get that circumference equals pi times the diameter. That's one version of our formula. But also, since we know that D is diameter, so 2 radii, we can also replace D with 2r. And so another common formula for circumference is to go, instead of pi 2r, it just makes more sense to go 2 pi r. And so these are the two formulas that we most commonly use. One formula just uses the diameter, and one uses the radius. But they're pretty much the exact same thing. So we have those two formulas here. Either you're going to have circumference equals pi d, or circumference equals 2 pi r. So based on that, we're going to do example 4, and it says find the circumference of the helipad described at the left. So in your textbook, there's this little real world link thing on the left side of the page. It's kind of small, but here I've made it a little bit bigger. It says in 2005, Roger Federer and Andre Agassi played tennis on the helipad of the Burj Al Arab Hotel. I probably totally butchered that, I'm sorry. In the United Arab Emirates, whatever. The helipad has a diameter, this is the important part, the helipad has a diameter of 79 feet, so our diameter is 79 feet, and it's nearly 700 feet high. But we don't really care about the height, we only care about the circumference, so that's only the distance around, and so all that really matters to us is the diameter is 79 feet. So because we don't have the radius, we don't need the radius, we can use the first formula, which is C equals pi times D, and we can just go C equals pi times 79, or basically 79 pi would be the exact answer. And if you wanted to find the approximate answer, you could take your calculator and go 79 pi, and you would get roughly 248.19, and this was in feet. That would be the circumference of that arena or helipad that they've got going on for us there. Beautiful. Alrighty, so now you can do it yourself number 4. If I can get my screen to do what I want it to. There you go. Do it yourself number 4. And then we will go on to example 5. And in example 5 it says find the diameter of a circle to the nearest hundredth if the circumference of the circle is 106.4 millimeters. So all they're really asking us to do in this case is to basically go backwards. Normally we're trying to find the circumference given the diameter or the radius. This time they're giving me the circumference and they want me to find the diameter. So because I know that the circumference is 106.4 and we know circumference equals pi times diameter, all I'm going to do is replace the circumference with what they gave me, and all I have to do is solve for the diameter. So this is pi times diameter. Don't let the pi confuse you, it's just a number. So if you had 5 times d, the opposite of timesing is dividing. So we're going to divide by pi. Remember, it's just a number. So the diameter, it says to round to the nearest hundredth. So the diameter would be 106.4 divided by pi, and you would get roughly 33.87, and that would be in millimeters. Okay? And then it also wants, that's all it wants. I thought it wanted the radius as well. It doesn't want the radius, but if it wanted the radius, all I would do is take my diameter and divide it by 2, which is good for you to know because in doing step number 5, they are actually asking for the diameter and the radius. But you're doing much the same thing with one extra little step there for you. So anywho, you can finish that little guide. And then we will go to our last concept and our last example. And our last concept deals with inscribed versus circumscribed polygons. So remember, a polygon is those things that I told you before have sides to them. So a polygon is considered inscribed in a circle if all of its vertices lie on the circle. So right now this quadrilateral, which is quadrilateral LMNP, so these are the 4 vertices of the quadrilateral, and they're all on the circle. So that was what we call a inscribed circle. So a circle is circumscribed about a polygon if it contains all the vertices of the polygon. So there are basically 2 different ways of saying it. So notice that in the first sentence here is talking about the polygon. The polygon is inscribed in the circle, but the circle is circumscribed about or around the quadrilateral. So it's basically a matter of how you're going to say it. If you want to talk about the quadrilateral, then you're going to say that it's inside the circle. But if you're talking about the circle, you're saying the circle is outside the polygon. That's basically the difference between saying inscribed versus circumscribed. Okay, so polygons are inscribed, circles are circumscribed. So just wanted to clarify that for you. So now we're going to apply this in our next example here, our last example, if this will go away. Okay, so here we have example 6, and it says a square with side length of 9 inches is inscribed, so the polygon, the square, is inside circle J, and all the vertices should be on the circle, and it wants us to find the exact, and that is the key, because it wants the exact, not a decimal, the exact circumference of circle J. So you're probably thinking, what in the world, how am I going to figure this out? The first thing you want to do is to actually draw yourself a diagram. So here's a diagram. You have to draw your own in most cases, but here it's drawn for you. So we have this square, and all the vertices have to be touching the circle. And then we know that it's a square, so all the sides are going to be 9, 9, 9, 9. And so the diameter is going right through the center. And so they want us to find the exact circumference. And circumference is pi times the diameter. My job is to figure out this diameter. And what I know is that this is a square, and so this is a 90-degree angle, and all of them are 90-degree angles. And if I'm going to cut this in half, this is going to be a 45, 45, 90. And we know that's a special right triangle, and when you have a 45, 45, 90, you have side, side, and side root 2. So we know that the diameter is 9 root 2 based on the 45, 45, 90 special right triangle formula from the previous chapter. So now we're just going to plug that in. So it's going to be pi times 9 root 2, and then this is going to be in inches because we have inches here for our units. And so now we just want to write it. We want the exact answer, so we don't want to multiply the root 2 or the pi. But we don't like this. This is kind of weird where you put the pi in front of the number. So we're going to go 9 pi root 2 inches. So basically you always want to put your numbers, then your pi, and then if there's any radicals, you put the radicals after. That's kind of the normal way of how to write your solutions. Okay, technically it doesn't matter if they're in the wrong order, but if you want to be consistent, you want to always put the integers or the numbers, then the pi, and then your radical if you have one. You won't always have one, but there you go. So the answer here is 9 pi root 2 inches. And now you can do your do-it-yourself question. And once you have completed this question, you will have completed your notes for this lesson. And I will see you in class. And thanks for watching.